Woosok Moon is an assistant professor in the Environmental Atmospheric Science Department at Pukyong National University. He got his PhD with my postdoc advisor, John Whitlofer, at Yale. And before that, he got his undergrad degree from Seoul National University. From 2017 until 22, he was also an assistant professor in both the Stockholm University Mathematics Department and the Nordic Institute for Theoretical Physics. And he works on he works on geophysics, but from an applied mathematician's using applied mathematics tools, including differential equations and recently machine learning with Sunhua and so on. So we're very glad that he's here. He's agreed to talk. He's going to talk about a recent paper in the proceedings of the National Academy of Sciences of the US, which is a very nice paper. So over to you, Woosok, and looking forward to your talk.
Yeah, thank you very much for inviting me, and thank you very much for introducing me. Okay, so thank you very much for coming to my talk, and then I will try to deliver my message clearly with easy language. So normally I'm a kind of applied mathematician, so it could be quite technical, but yeah, today I'm going to try to deliver the right implication about this result. So today I'm going to talk about the large scale atmospheric dynamics, which might be strongly related to global warming situation. And then we can think of what would happen in the future in this climate, especially large scale atmosphere. So mid-latitude, maybe away from the tropics and the mid-latitude, the most important dynamics we have to understand what's going on in the global warming is a jet stream meandering. Jet stream is not static; it's always meandering. The meandering is actually caused by the willing to transfer the remaining energy in tropics to higher latitude. That's the main purpose of meandering, but unfortunately, it is very chaotic. It looks like that. I'm not saying it is definitely chaotic, but it looks like a chaotic, like a complicated structure, like these pictures. But somehow we have to understand this dynamics, and then we have to understand the role of this meandering, and then in the future we have to predict that because it is related to extreme weathers. So actually, that meandering is a quite classical topic in climate science and atmospheric dynamics, and for a long time, and that is the main topic for weather forecaster. So, in every graduate course in atmospheric science, jet stream is the main topic. But nowadays, it has been really focused because it is strongly related to extreme weather in mid-latitude, the extreme flooding, extreme drought, wildfire. Everything should be related with a jet stream meandering. But how this one is connected with global warming? The logic is very simple. So if I say clearly, for example, 40 years ago, 30 years ago, but at the time, Arctic, higher latitude, because of enough sea ice and land ice, it was really cold. In the case, the most important quantity for the dynamics is a temperature difference between polar area and tropical area. But at the time, the temperature gradient was larger. And then someone claimed that it is stable. So jet stream does not meander seriously. From time to time, meander that was generating typical weather in mid-latitude. However, under global warming, after 21st century, so Arctic sea ice decline quite seriously, which means temperature in high latitude rise quite seriously. But and then temperature gradient between polar area and tropical area decrease, and then people argue that it caused some less stable situation for jet stream. And then jet stream starts to meander. This meander causes extreme weathers. If you look at this meander, this area, the wind is going from the tropics to the polar area, which means some hot and humid air is moving from lower latitude to higher latitude, and this area might cause extreme flooding. The other area is reverse, very dry, cold air coming down, and then it is causing very dry weather, which is strongly related with wildfire over there. So somehow, when I look at this situation, when I just listen about this explanation, I could not understand because this logic was not logical to me, because there is no dynamical, perspective, dynamical, investigation about this one. So I thought it was a bit weird. And then 3 years ago, I determined to get into this field again. So a long time ago, when I was in Penn State as a master's degree student, I was doing this field. But at the time, I was very disappointed by this field because it was too complicated, no, further understanding after running tons of model. And then I determined to, going out of that field and then forget about that. And then I did Arctic sea ice research. But suddenly, 3 years ago, I entered this field again with a different perspective. So because I was a beginner, I started from the real basics. What is the basic? Basic is a synoptic storm life cycle. So Baroclinic wave life cycle. In the middle latitude, the most basic thing is jet stream is meander, and then low pressure system is generated, and then that low pressure system starts to move, and then generating some rainy, area, and then some mixed up that area. Mixing up means energy is transferring from low latitude and higher latitude. If I just summarize that one, so normally baroclinic wave, the jet meander start from the surface by baroclinic instability. Baroclinic instability happens with a strong wind shear, which is proportional to temperature gradient between north and south. And then this one is start to grow and then started migrating upward. During this migration, the heat is exchanged between lower latitude and higher latitude, so polar heat flux is going to be generated. And then wave just goes up and then travel near the tropopoles, and then over there they start to move to tropical area, and then right here, and then they start to break, and then this breaks generate the momentum flux, and then the eddy give the energy back to the mean flow. And then it is typically represented by the cold front, warm front movement. So, based on this structure change with the time, in mid-latitude countries, we are doing weather forecasting. So, and then this one is going to be represented by Baroclinic wave life cycle. Here it is a famous energy diagram between mean field and eddy field. They are exchanging energies. During this exchange, this wave life cycle is determined. That's the kind of basic of mid-latitude dynamics. And then to understand or to see what's going on in mid-latitude in some climate perspective, people start to make an index. And then that index representing some dynamics. And then they just look at the temperature change of the index. And then that temperature change of the index represents the change of the mid-latitude jet stream or some other life cycle field. And normally people like southern hemisphere because the land-sea contrast is not that serious. So it is very close to some simple theoretical idea. So, and then they start to look at the jet stream behavior using index. One of the famous one is SAM. SAM is Southern Analog Mode. And then this one is constructed by upper level jet stream because it's the strongest wind exists upper level around 200 millibar. And then based on that quantity, they made an index. So because of that, this SAM is strongly related with upper level processes. What is upper level processes? Jet stream exists. And then as I explained, wave breaks on the equator side of the jet, and then momentum flux is generated and then giving the eddy energy back to the mean flow. That's the main process. Because of that, this SAM is closely correlated with momentum flux and then zonal mean wind. But recently, it was a quite index which was really popular and still popular. And then recently, Thompson and Woodworth introduced the other index called Baroclinic Analog Mode. Instead of upper level process, they focus on lower level process. So forward heat flux. So storm is generated initially, and then that is the kind of a the basic the process. And then this index instead of the jet stream, the index is correlated with eddy kinetic energy and forward heat flux. So it represents the lower level process. But and then today, I really want to focus on this lower level process because this lower level process is strongly related with precipitation, the weather. Okay, so, and then if I look at the temporal variability of this quantity, the BAM index, which representing the eddy kinetic energy, forward heat flux, and then maybe precipitation, if I just look at power spectrum, it is very, very interesting, because this is the analog mode, the southern hemisphere. And this analog mode, if we track down the temperature change and then make a power spectrum, and then you can see a very dominant peak exists, which is located around 25 days. 25 days. I mean, think about it. Specific peak in the power spectrum represents some oscillatory behavior, oscillation. Very easy to predict, very regularized motion. And then that one exists around 25 days. Even though SAM does not have that kind of things, but BAM has a very specific peak, and then it is strongly related with precipitation. But then, I mean, think about it logically. 1967, the Lorentz said that the weather is very chaotic. Chaos. So after some time, we are going to lose our predictability because of chaotic characteristic. That's the kind of a limitation of our prediction. Because of that, I don't look at the prediction after 5 days. Normally, I don't trust that. I mean, that's the nature of the atmosphere. But 25 days means we are piling up the weather situation again and again, okay? And then, 25 days reaches. And think about it. The chaotic situation piled up and then generated oscillatory behavior. I've never seen such a phenomenon in physics. Maybe, piling up the chaotic situation might be close to random number generator. But suddenly, regularized the motion just came out 25 days. And then I think it is very, very peculiar. Oh, wait a second. Huh? Okay. So if you look at the forward heat flux, it is a southern hemisphere. If you look at that, I mean, strangely, this forward heat flux shows up and down, which may be very close to some oscillatory behavior. I mean, I just want to look at directly from the data. And then this one, could be summarized by power spectrum analysis, 25 days a peak. And then I just started to wonder, I mean, as a applied mathematician, I mean, what kind of equation set I have to use to investigate 25 days a cycle? I mean, what is causing this one? I mean, it is a mystery to me, and then I want to really find out. I mean, that was my first question when I entered this field. So what can I do? I have to go back to real basic of climate science, and then I have to re-evaluate what I have learned. I mean, that's what I did. So, I mean, think about it. College students, first year, they might listen climate, very basic course. But in the case, they learn this one, simple climate model. I mean, this one is actually very simple because Earth is a point object in the universe, and maintaining some thermal equilibrium. So in the case, incoming solar radiation and outgoing long-wave radiation make a balance. And then what we could get is average temperature. I mean, that's very simple, a basic physics law. But and then if we magnify that point, and then we realize that this object has an imbalance of energy flux. So near the tropics, surplus exists, and near the polar area, deficit exists. And then by a simple physics, we have to expect that this surplus of the energy should transfer to the polar area. So In the case, as a mathematician, the main equation should be maybe very close to forced heat equations like that. But actually, Gerard North, 1975, used this model to talk about the stability of the ice sheet. And then here, important thing is this diffusion term. It is a kind of, this term is transferring the energy from a high energy area and low energy area. And then this a simple term just summarizing, all of the complicated, feature in the mid-latitude eddy dynamics. Everything is going to be contained in this simple coefficient D, eddy diffusivity. But somehow, in this purpose, for this purpose, I think it is a very logical model, right? And then if I magnify the mid-latitude, main dynamical equation is quasi-potential vorticity equation. So vorticity equation, the fluid is rotating, and then we are describing that. I mean, that's the main equation, because our low pressure system, high pressure system, it is vorticity in fluid dynamics. And in this equation, potential vorticity conservation, that is the basic equation describing the dynamics of mid-latitude. And then out of this one, I mean, we could find the baroclinic instability, the main mechanism for generating the weather system. And then that's what I have learned during, atmospheric science major. But and then I just placed, maybe more model might exist, but I think it is really basic. And then more model might be just a, variant of this kind of a models. And then I think it is a basic. But and then I placed all of them in one slide, and I started to look at it. I mean, think about it. Here is energy flux version of the models. This one is a vorticity models representing the dynamics. Here, there is no dynamics. And maybe this model is for some situation describing at least the season. So the time scale is, should be longer than season. Season is the kind of a minimum time scales to use this kind of a, model. And then this one is weather. Weather is in mid-latitude has a time scale like 1 or 2 or 3 days maximum. But and then, I mean, previously, I showed the power spectrum showing the peak 25 days. And then 25 days is shorter than this season, but larger than, weather. And then I suddenly ask myself, what kind of equation, what kind of physics exists here? I mean, what is it? I mean, do I have to rely on QG dynamics and kind of to explain 25 days a cycle? But that was a little bit unreasonable under these given conditions. And then I think some of the things might exist. And then that was my, first mystery. And then I look at the, scaling argument. In fluid dynamics, it is very important to find out major scaling. And then I did a scaling analysis of mid-latitude mean velocity from the geostrophic balance. I mean, geostrophic balance is the basic balance in the mid-latitude. And then I used this geostrophy. I started to scale the mean zonal mean wind magnitude. And then I'm not going to go into the detail, but the most important thing is this mean velocity should be proportional to the meridional temperature gradient, temperature difference between high latitude and low latitude. But and then if I just put up some typical values, I could find 30 meters per second as a mean velocity. So it seems quite logical. And then I introduced some small parameter implying the long-dimensional meridional temperature gradient, alpha. And then U should be proportional to alpha. And then to define the dynamics, and typically, historically, we use Rossby number. Rossby number should be small for the large-scale atmospheric and oceanic dynamics. And then I find Rossby number, small Rossby number. And then this Rossby number has a relationship with alpha, meridional temperature gradient. And then there is a prefactors in front of that. And this coefficient is very interesting because it has a very specific length scale and also length scale we are going to choose. If I look at that, alpha is going to be L squared over LD squared and epsilon. So LD is defined as a square root of GH over F. G is gravitational acceleration. H is typical depth of the atmosphere. F is a Coriolis force parameter. And then this is around 3,000 kilometers. And then this one is known as external Rossby deformation radius. But and then if I look at this one, I mean, largest scale in atmosphere means larger than 1,000 kilometers. And then if I choose L is around 1,000 kilometers, it is a storm scale, synoptic storm scale, 1,000 kilometers. And in the case, this L over LD square is going to be around 1 over 9, close to 0.1. And epsilon is normally 0.1. And then in the case, alpha is going to be the order of epsilon square. However, if L is chosen as LD, in the case alpha is order of epsilon, which means according to asymptotic analysis, I think depending on the L, 1,000 kilometer or larger than 3,000 kilometers, the alpha, the scaling of the alpha based on epsilon will be changed, which might imply that there exist two length scales. At each length scale, different physics might exist. That's my guess. That's my guess. But in the case, according to the basic fluid dynamics, I have to do long dimensionalization after choosing specific length scale, and then I have to simplify the given Navier-Stokes equation, continuity, and heat equation, and then try to find the governing equation, some good approximated equations. So when I choose alpha is epsilon square order, and then if I do get that long dimensionalization and then simplify the everything based on perturbation analysis, I'm not going to go into the detail, but after long calculation, what I could find out is the major dynamics is potential vorticity conservation equation that I mentioned, the basic equation set for Baroclinic instability, storm generation. So it is weather equations. However, if I choose epsilon order, alpha is epsilon order, and then do same things, different set of equation comes out as an approximation. So it is but actually if I just look at the equation is so velocity field all satisfied geostrophic and hydrostatic, and then the continuity equation comes down to Sivadrov relationship. The beta effect is really big, and because of that, the vertical movement, vertical field should be balanced by meridional field, meridional beta effect. That's the Sivadrov relationship, which is crucial for ocean circulation. But and then the last one is a heat equation. And then that's the kind of this whole approximation is called planetary geostrophic motion. But I'm not the first one who find this limit. I mean, long time ago, 1950, the very famous atmospheric dynamist, like Phillips, already mentioned this one in his review paper. He said in large-scale atmosphere, two types of geostrophic motion exist. And then he said one is a type 1, which is a QG dynamics one, that QG vortice dynamics, and then he said other one, type 2. That type 2 is implying planetary geostrophic motion. So somehow, after some time, this planetary geostrophic motion was disappeared in this field, was not that popular, and then forgotten. Maybe after that, the model simulation became really popular and the main tool, and then people started not to use this one. So, and then almost gone. And then I just refound this one again. So now I just want to put some different implication for this large scale motion. The other thing is that, so I have to focus on is how to represent the coexistence of the two scales. It is also mathematical, the mathematical scheme called multi-scale analysis. And then I have to include two scales at the same time by introducing the new variable in time and spatial domain like that. So here, capital letter represent planetary scale variables, and then small alphabet represent synoptic scale variables. And here is epsilon is representing the ratio of the two length scales. And then I'm going to change the differential parameter in this way, and also the pressure and density and temperature field divided by three parts: the hemispheric mean, planetary scale part, and synoptic part. And by this distinction, I put this formalism into primitive equation, Navier-Stokes equations, like this right-hand side. It is quite complicated and very long calculation. And then I collected order by order the balances. So what I could get is this one. So if I summarize this one, is like that. These two scales, these two geostrophic motions, definitely must satisfy basic balance: geostrophic, hydrostatic. And then planetary scale must satisfy Sivador relationship. And then these two scales meet in the heat equations. Okay? In the heat equations, these two scales meet each other and then start to interact. So this is synoptic activities acting as a forcing, thermal forcing for the planetary motion. And then for synoptic dynamics, we need vorticity equation. If you look at these vorticity equations, these planetary variables act as a kind of mean field for the synoptic values. So the whole thing could be summarized by this diagram. Two geostrophic motion exist: the planetary geostrophic motion and quasi-geostrophic motions. And then the external thermal forcing exists to drive the planetary geostrophic motion. At the same time, huge motion, this kind of synoptic storms, are generating the heat flux convergence right here. And then planetary geostrophic motion providing the mean field for the huge motions. And then planetary geostrophic motion give the mean field, and then maybe unstable, and then it could be meander and then generating instability, and then that instability generates the huge motions. And at the same time, these huge motions change the mean field. So they are interacting each other. Maybe it is the description of the mid-latitude dynamics. Jet stream and then eddies, they are interacting each other. And maybe by that, multi-scale formalism, that's what I find. So now the question is, okay, this is a kind of a formalism I'm thinking. This is the kind of a mathematical way of describing the mid-latitude dynamics. So in the case, my question is, okay, how the global warming can affect this mid-latitude dynamics? The first thing that I have to do is, how planetary geostrophic motion react to some thermal forcing. Because it is providing the mean field for the weather systems. So I just want to know how this mean field is going to change under some update by global warming. That's what I wonder. So what I did is I assume that there exists a mean field, some zonal mean wind exists, constant field, even though it is an idealized one. I just assume that it is a constant mean wind. This mean wind kind of magnitude representing the polar area and tropical area temperature difference. If the temperature difference is big, and then U is going to be big. And then the temperature gradient is weak and U is lower. That's the assumption. That's again, kind of a mean field. And then I just start to think of a perturbation out of this one because of a zonally asymmetric some forcing, kind of a land-disk contrast or some of the forcings. That's the QR. And then I just want to look at how this planetary geostrophic motion reacted to this steady forcing. Maybe this one could give us some idea how mid-latitude atmosphere react to some global warming. Okay, so it is a mathematical. However, motivation is quite clear. I just want to find out the connection between mid-latitude dynamics and the global warming, which is generating the high temperature in higher latitude. But and then, this one is kind of could be solved quite easily. And then the last one is kind of a final equation for this one. The second order with respect to Z, and then the right-hand side is non-homogeneous term, represents the summer forcing. And here, Gx is actually a summer forcing structure. Fx is x integration of the Gx. I will tell the importance of this one later. Somehow this one. And then, anybody could solve it with proper boundary conditions. Boundary conditions normally are given to the vertical velocity. So I can think of a two rigid boundary, like on the bottom, and then on the top is might be, tropopause, and then rigid boundary, and then W is 0 on both of them. And then the solution, the response, actually is dependent upon the size of zonal mean wind magnitude. There is a threshold behavior. As you can see, it is a second order differential equation. So depending on the characteristic equation, oscillatory behavior or decaying behavior exists. So definitely that one is realized by physically the size of the U and some threshold value determined by beta effect and static stability S. And then if U is bigger than threshold, if you look at, you can focus on this one. So lower level, pressure field. So, and then you can see that the wind is following parallel to this contour. So, and this mean field a little bit wavy, right? Well, upper level also, a little bit wavy. However, if U is lower than a threshold, you can see the very wavier, the mean state. Very, fluctuation quite serious, even though I'm just giving the same forcing on the surface. And then I can think of a different boundary conditions. So lower level is 0, however, upper level is just a decaying kind of a radiation conditions. And same thing, depending on the size of the U, the behavior, response of the atmosphere is going to be quite different. With a large U, as you see, lower level, a little bit wavier, but upper level is almost zonal. There is no, wiggling in here. However, if U is smaller than a threshold, you can see this really wavier, situation in the mean field. Even upper level shows quite serious waviness. So, however, think about it. It is a very, approximated theoretical argument. I simplified that complicated Navier-Stokes equation and then just solved some solvable equation and then argue that if U is lower, which means Arctic is quite warmer, and then because of that, the U wind is quite lower. So in the case, mean state is going to be really wavier due to some surface forcing. That's my argument through this analysis, but I have to check out if it is really true in, primitive equation, Navier-Stokes equation. So we designed GCM, dynamic core simulations. So this one is kind of using full Navier-Stokes equation. Only difference between this one and real GCM is physics. So this idealized GCM use very simplified physics, like a cloud or precipitation. Everything is very simplified, unlike real GCM. But still, equation set, whole equation set is a full primitive equation, Navier-Stokes equations. And then we control the whole dynamic field by surface heat flux. We just put the specific surface heat flux to control the overall dynamics. And then first, we give the Arctic warming and cold for the comparison. And then we put the zonally-asymmetric forcing representing land contrast wave number 2 in the middle latitude. And then after putting this one, definitely surface temperature showing that this one is a very warm Arctic, warm, middle latitude somewhere. This one is very cold Arctic. And then again, very weak period, wave number 2 forcing exists. Let's look at the response. This is the response. And the first one is mean field, warm Arctic case. Because of the warm Arctic, if you look at the jet stream is really weak. And then conversely, this one shows the very strong, jet streams. And then let's look at the response of the atmosphere because of the surface thermal forcing. This one is upper level. This one is lower level. And then you can see quite magnified geopotential height response. However, in the strong wind cases, strong jet stream cases, the response is quite small compared with this one. That's quite consistent with a simple theoretical argument. And then also interestingly, this one is a meridional wind, upper level, lower level. This one is a vertical velocity. But this one is omega, so omega negative means upward motion. So, and then in this category, this one is for the warm Arctic case. This other column represent for the cold Arctic case. And then interestingly, if we look at the comparison of upward velocity, this one is very much organized following the wave number 2 structures, but this one shows a very not organized, some complicated structures. This organization is very interesting because organization means here is upward, downward. Upward means is a kind of a very good condition for the precipitation. This one is a very dry condition area. And then area distinction exists by the mean field, and then maybe some preference exists for precipitation or drought, maybe, okay? And then this field, lower level and upper level, they are satisfying Sieber-Drop relationship. That is the most important thing. So, and then again, as I mentioned, I mean, we did several experiments, we could control the zonal mean, zonal wind by surface flux. So we control that, and then we can just observe the stream function amplitude. And then as you see, like the theory predicted, zonal mean wind is decreasing, stream function amplitude is increasing. So maybe global warming might cause the zonal mean wind is decreasing, and in the case, response of the atmosphere, could be bigger. I mean, might be the direction toward global warming in the mid-latitude. So, and then again, we did another experiment. I mean, if I just show the solution form, I mean, there exists the fx. Gx is a summer forcing form. Fx is integral of that. And then the response is proportional to fx. Fx is actually integral of the gx, which means it is proportional to 1 over k. K is wave number. So this one is interesting. So because as wave number increases, some wave number 2, 3, 4, 5, and in the case in response, that component is going to decrease as k increases. So if we just put some local forcing, maybe it is more realistic. Maybe some locally, like Siberia, the snow melts quickly, but in the case over there, quite a magnified heating exists early spring, early summer, something like that situation. But in the case, if we look at the response of the atmosphere in a stationary sense, we can see that wave number 1 in the upper level is really, specifically dominant. It is exactly following the simple theory. So now, I have to conclude that. Well, I mean, I just made some formalism to represent the mid-latitude or, jet stream dynamics. So 2 kinds of geostrophic motion exist, planetary geostrophic motion and QG dynamics, and then they are interacting. Especially planetary geostrophic motion providing a mean field in the mid-latitude and then have a role to generate the synoptic eddies. But it is acting as leading order dynamics, for some, some summer forcing. And then we can see that response is strongly related with zonal mean wind magnitude. And then that magnitude might be strongly related with Arctic warming situation, which is caused by global warming. And then as U wind is decreasing in the mid-latitude, the response of mid-latitude atmosphere on the some summer forcing will be magnified. And then that might be strongly related with extreme weather situations like flooding and drought, wildfires. So what I can say is maybe under global warming, this situation will be more serious. And then we can explain that simply by this formalism of dynamics. Thank you very much.
Thanks, Woosok. The floor is open for questions. I think Shiba can take over and read questions from a sheet that people have been writing it in. Is that right, Shiba?
Yeah. But I don't see any questions there as of now. So I would request the attendees, if you have any questions, you may kindly switch on your videos and directly interact with Dr. Moon.
Yeah, that should be okay. If nobody has a question, I'll ask one first.
Yeah, please go ahead.
All right. So, Woosok, can you the last bit about the k equal to 1 mode being dominant? Can you explain that bit again? Where do we see this in the atmosphere?
Okay, if you look at this solution, this C is a pressure field, kind of a response, the pressure field. And then if you look at this whole solution forms, it is proportional to F. As a matter of fact, this Q is summer forcing we given, original form. And then F is represent the response. But F is integral of the GX. Okay, and then let's think about in terms of Fourier, decomposition. And then in the case, if the GX is proportional to some, sine and cosine KX, after integration, the FX should be proportional to 1 over K. Right? So which means K is increasing, F is decreasing.
Yeah.
Okay. So, and then if I apply this local forcing, it is like a delta function, like, local forcing. So as a matter of fact, if we want to represent this one by Fourier series, we need a lot of terms with maybe equal magnitude. However, the response is integral of them. So in the case, the integral should be proportional to 1 over K, right? So which means wave number 1 should have a bigger magnitude than other waves.
So even if if I understand this right, even if the land-ocean contrast, temperature contrast is in one place, the response will be the same across all the longitudes. So the response will be the k equal to 1 mode will pick up across all the world. The whole zonal region will be okay.
Yeah, kind of normally, think about it realistically, the summer forcing at some point could be quite point forcing, Siberia warming and some of the warming, but the response will be quite, very planetary scale, lower, low wave numbers in the upper levels.
Yeah, that's very, very nice. If I can ask another question. So maybe what people can do is raise their hands, and Shiva can call on them as they raise their hands. So before people raise any hands, I'll ask another question. So you've considered temporally constant function of X temperature forcing, right? But the land-ocean temperature contrast could go up or down. During the day there could be a maximum temperature contrast, and during the night there could be no temperature contrast. So is that something you think can be easily incorporated into your thing, like a temporal fluctuation of the temperature contrast as well?
I mean, here, yeah, it's right. I mean, I didn't consider about the, temporal change. I mean, I assume that it is a little bit, stationary sense, because I'm considering about the time scale, which is bigger than weather. And then I just want to find out. And then think about it. Our situation is like that. I mean, for example, wave number 2 forcing, I mentioned several times, it might be related to land contrast. I mean, it is always given in our hemisphere, especially in northern hemisphere, right? It is always given at some point, summer and winter, always. But the only difference in large scale perspective on the global warming is Arctic is warming faster than any other areas. That's Arctic amplification. But in the case, maybe a lot of complication exists. However, what we can think is this temperature gradient between the Arctic and tropics is declining under global warming, and then it should be represented by decrease in the zonal mean wind. In the case, land sea contrast is always given, and then how the atmosphere responds. Then what I'm saying is if you decrease, response will be bigger. In the case, field is has more vigor, and this vigor should be related to extreme weathers in mid-latitude.
Yeah. No, that reasoning is clear. It came through really nicely. Vishal has a question, please.
Yeah, Vishal.
Thanks a lot, Woosok, for this nice talk. It was very interesting. I didn't follow it in the second part, but for the first part, I have a couple of one question and one comment. The question is related to actually, so you showed that there is a difference in the scales. On one hand, you expect something on seasonal scale, but you have QG theory for like a weather scale. And a cascade has to happen one way or the other, and you found that there is a 25-day mode that could bridge this gap. So my question was, then in some sense, are you assuming that geostrophy in the strict sense is valid across the scales larger than QG weather scale?
I mean, if the scale is larger than weather scale, 1,000 kilometer, that geostrophy hydrostatic balance always is satisfied. It's not going to change. Yes. But what I'm saying is that planetary geostrophic motion has a different structure compared with QG potential vorticity dynamics. So if you look at the main equation, think about it. When the weather scales, this whole equation represents some potential vorticity. That quantity exists. That quantity is preserved with motion. That's the main dynamics right here. Yeah. However, this planetary geostrophic motion is totally different one because main equation is a heat equation. Yeah. Okay. And I think about it right now. I mean, when I draw these figures, this one is a vorticity. This one is a heat equation. And then I'm saying here, planetary geostrophic motion should be here. That one is a heat equation, is the main equation with dynamics. I mean, think about it. This one is a heat equation with dynamics. This one is a dynamics. This one is a heat equation. So I'm just saying that planetary geostrophic motion is the right one standing in between. That's my point. Okay?
Yeah. Okay. My second thing was, so we in India experience monsoons, and monsoons is a bit, I mean, if I were to kind of think of monsoon question, it has some analogy to the question you were looking at. So there is a seasonal scale envelope, and there is a small scale synoptic scale variability. And we also see some intermediate scale variability, which we call intra-seasonal, which is 10-day to 90-day. But there is a nice cascade we see, and each of these different time scale behaves a bit different than other. So do you think this is because we are in tropics? That means Coriolis force is small and it's not imposing really strong geostrophic constraint, and there's more scope for moving away from it. And
actually,
if yes,
that's what I'm doing right now. I mean, you're in tropics, so because of that, I mean, dynamics is a bit different compared with the mid-latitude, because here in this equation, for example, F, that Coriolis parameter is going to convert it to 0 as we approach to tropics. And then because of that, the dynamics in the tropics are a bit different from mid-latitude. But still, what I'm thinking, okay, it is just my intuition. I'm not saying it is true, okay? But because you mentioned monsoon, I think monsoon is multi-scale. That's my guess. First of all, I mean, India has shown the very regional monsoon phenomena, land is contrasted. However, monsoon could be understood as some global scale response in the tropics. I mean, if you look at the whole tropics, there exists really big motions like water circulation. I think water circulation is also kind of a monsoon in terms of land contrast. So I think Indian monsoon, to understand the Indian monsoon, I think it's just the regional dynamics cannot explain whole aspect of the monsoon, and that one should be explained by multi-scale dynamics, okay, global monsoon and regional monsoon, and then at the same time, we have to consider about the interaction with mid-latitude dynamics. So I think the monsoon is a very interesting and very complicated problem. But what I'm thinking is under some formalism perspective, if somebody could explain or find some formalism, mathematical formalism or physical formalism to describe the Indian monsoon properly, I think that's going to be the basic fundamental to describe atmospheric motion entirely, because it contains everything.
Yeah,
okay?
yeah.
That's my perspective.
Yeah, thanks. So a related question maybe which is related to monsoon. So we also think that the cloud clusters that form and survive for significant time, they at some point could actually bring a different time scale into the mix. And in terms of your heat equation, I feel the heat equation could have several time scales already embedded, which are related to maybe cloud clusters. So would like to hear your kind of opinion on that.
Okay, if I just say, okay, my just perspective, it is not definite answer. So interestingly, in tropics, a cloud cluster could generate different time scales, like MJO. Okay, it is a coupling between thermodynamics and the dynamics, and then I think a Kelvin wave is affected by the cluster of a cloud, because the cluster of the cloud could generate some summer forcing instantaneously over there. And then this cloud forcing is quite important to understand the temperature change of tropical dynamics. But it's a very challenging problem because, as you know, cloud itself is multi-scale. The size is 10 kilometer, but somehow this precipitating convection has a very, very interesting characteristic because it just draw in one region and then make a cluster. I mean, actually, in terms of convection, idea, the making the cluster is also quite interesting phenomena. So
Agreed.
I think that's another difficulty to talk about monsoon, I guess.
Yeah, indeed.
Yeah.
Yeah, thanks a lot, Woosok.
Thank you.
Professor Anshuman has a question. Anshuman? You there?
Hi, Usuk. Thanks for the seminar. It was really nice. I have a question, I mean, which you can say that it is similar to Ravi's question. So you set up your model based on the southern hemisphere, right? You say that because you have the Southern Ocean, it is much easier because you don't have much land. But I see your figures and plots mainly over the North Pole. So, so how do you take care of the land-sea thermal contrast?
Here, I mean, I'm not, referring southern hemisphere. It is general, hemispheric dynamics. I'm not choosing any hemisphere, okay? First one. And then here, that's very good question, okay? So here, I assume that, think about it, in this formalism, zonal wind is dominant, and then zonally asymmetric one is smaller. I mean, it is due to theoretical, convenience, I chose that. But in northern hemisphere, actually, it is not true. Maybe this zonal mean wind and zonal asymmetric part might have the same magnitude. That's the difficulty to investigate the northern hemisphere. What I'm thinking now is kind of a this formalism. I mean, it's not necessarily, the hemispheric size. I mean, we can apply this formalism locally, because the length scale is just 1,000 kilometer and 3,000 kilometer, which is quite enough to cover some, continent or some section of the, land contrast area. So I'm just thinking to apply this formalism locally, for example, Pacific area or North Atlantic area. because this length scale is quite enough to contain this multi-scale formalism. So actually, northern hemisphere has that kind of a regional characteristic. Not all of them. Maybe southern hemisphere we could understand it in whole hemispheric, variability. However, northern hemisphere is a bit different. So I mean that's kind of my future plan, how to attack the northern hemisphere situation properly.
Thank you very much.
Thank you.
More questions?
Anyone else? Any of the other attendees have any questions? Okay, if not, then I would request Professor Ravichandran to close this. We should click a picture before we close the session.
All right.
I would request all attendees to please switch on their videos.
If you're feeling brave, you can make a face while she clicks a picture. Shiva, say when.
Noka, Devasmita, yeah. Many of our students are online. Pooja, you're there? Can you just take a picture? My screenshot, no, it just misbehaves sometimes.
Yeah.
Yeah, thanks, yeah. Request all attendees to please switch on their videos. Pooja, are we done?
Yeah, done.
Okay, thanks, yeah.
All right. Thanks again, Woosok. On behalf of everybody present, let me thank you
Dr.
again for
Moon.
an excellent seminar.
Thank you very much for coming to my talk. Yeah.
And
It was really nice.
I mean, whenever possible, do drop by. We usually give out mementos of, at the end of talks. So we can keep one in reserve for you. So whenever you come by, we will hand it over to you in person. So thank you again,
Okay.
and
Thank
bye
you.
everybody. Yeah.
Bye.
Bye. Take
Bye-bye.
care.
Thank you, Dr. Moon.